Okay, so first off, this one is a displacement time graph, not a velocity time graph. So we do have gradient equals to displacement over time velocity. So from 0 to 32, we would have okay, so my description will be for their um basically the gradient. So we have time equals to 0 to about 10 seconds. Okay, constant gradient, constant velocity. And we have from time equals to 10 seconds to 20 seconds. There's no gradient, so we'll say that the toy car is at rest. Or we can say that there's no velocity. So 20 to 32 seconds. This is a negative gradient, so there is a negative velocity. So negative velocity means that it's traveling in the opposite direction. So we say that it will move with a constant velocity, but in the opposite direction. With something like this. So the question here is asked about remote controlling of the toy car. So for remote control, uh, the standard one that we always use is infrared. Okay, that's all. Okay, I'll leave this here for uh, 30 seconds and we move on to the next one. Okay, okay, so for this case, Kelly, do you know which Newton's law explains this?
Is it an object only moves when a force is applied on it?
One of the things is about this. The skateboard move backwards while the person move forward. So it's kind of like he kick the skateboard backwards, but yet he propelled himself forward. So, which law explains this? If you talk about your when we are walking normally on the ground, right? Our our feet also kick backwards for us to move forward. It's the same narrative here. It's Newton's third law. So in this case, first off, we will explain that. Okay, I'll use SB as the skateboarder. So I'll mention that the skateboarder's foot he pushes the skateboard to the in this case you can see that it moves backwards. That means it actually kicks the skateboard to the left. And this causes the skateboard to move to the left. Okay, so this one is the applied force kicking it backwards. Then the law that we're using is Newton's third law. This is like a because you push the skateboard backwards, so the skateboard will push you forward. Kind of concept, just like how when we walk, we kick backwards in order to move forward. So since the skateboard is moving to the left, we will say that the skateboard you exert what we will exert a forward force. Okay, to the right. So this forward force that is pushes that is to the right will actually push the skateboarder to the right side. It's something like this. Okay, so this is more of a action reaction. Okay, let's look at part B. Useful energy that occurs as the skateboarder jumps forward. So when he jumps forward, he actually gains some height. So it's um from his own body, right? So he exerts the energy. So it's from Okay. Yeah, let me look for this. Okay, this is a mechanical energy. So this is through a mechanical change. Something like this. Okay. There's nothing much here. The last one is your KE. We have our half mv square, 42, 0.3 square. And then from here we get 1.89 joule. Haley, okay for question 2 so far?
Yeah.
Okay. You jot down whatever you need first. Okay, the dust work in air concept. We want to talk about, because work done will always be force times distance. So we need to talk about how he exert a force on the air and how the air actually moves. So we can say the skateboarder exerted a force on the air. How does he exert this? Generally because of his body. So his body is plunging forward. So with his body as he moves forward, and the distance portion is moving the air through a distance. Okay. One of the TYS question has talks about how does the swimmer does work on the water as he swims. In the same concept, I will change this to the swimmer exerts a force on the water as his body moves forward and then moving the water through a distance. It's the same concept. So whenever we want to talk about work done through a certain material, it will be something like this, easiest to explain. So eventually what happens to the work done by the water in this case? Because the water, as it moves, the energy eventually will be converted to other form. So most likely will be transferred into a heat store. Okay, something like this. Okay, if no question, take a look at number 3. Moments we talk about. Including things like line of action, whether it will cause it to topple and things like that. Okay, so does not topple, meaning that the force will actually push it down this way. This will be not topple. Okay, this is if the moment acts this way, then it will topple. So the line here will mention that the line of action of the weight. So we mentioned it's on the left side of the wheel that's on the right. So this will create your, the moment direction will be for this. This will be your anti-clockwise moments. So whenever you talk about the moment, you're always about what object. Although over here it says it's a period, but whether this thing will topple or not really depends on the reference to the wheel. So we say that it creates an anti-clockwise moment about the right wheel. And this moment will actually pushes the bus on the ramp, and because of this, it does not topple. It's something like this. Okay, let's move on to the next part. If we want to know the reason for a greater tilt of the angle, so this greater tilt of angle, if you see that this angle is tilted higher, the CG of this spot here will actually change. So assuming like something like this, then you'll see that the bus is slanted and will go something like this. So the CG generally will shift. So why in a real life context, the CG will shift? And because of this shifting of the CG, we need to test it. We need to test the stability depending on how much the CG has been changed. So clearly under what circumstances, right, the CG might shift and may cause it to topple under real life context. Let's talk about why the CG may increase, might be higher, for example.
Is it because like the wheels shifted?
Actually, the wheel is a constant one. The wheel doesn't change. How about the composition of the bus, right? The CG might shift due to the composition of the bus. We will want to understand that the CG is actually at the middle, but due to, let's say, passengers, normally it's the passenger sitting behavior that causes the CG to be not at the center, then this test will have to be more rigorous by raising the angle to test the stability. So how will the passenger sitting behavior change the CG position?
When like all the passengers are towards the back of the bus.
Like the can. So let's say to the back also, more importantly to because the thing is that when we shift, for example, right, if let's say a lot of passengers sit to one side, then let's say the CG is still at the same height, but somewhere here shifted to the right. You see, this one will cause it to be outside, then it may topple. So is the shift in CG can be caused by number one, more passengers sitting to one side of the bus. Okay, so the shifting to one side of it may cause it to be unstable, even though the slope is still the same, everything is still the same. So by increasing the tilt, we will know that it will help you to, increasing the tilt will help you to simulate like more passengers seated to one side. So it's like a simulation test. Yeah. So what about the situation? How would CG be raised higher, for example? So this one reason can be okay, but we can also offer another reason why the CG may be raised. How can the CG be raised? How will it be raised to a higher point? Again, it's passenger sitting behavior.
Um, when the passengers are like seated on top of the bus.
Yeah. So can be raised to a higher point. Keep more passengers seated on the upper deck than the lower deck. So again, this causes the CG to shift higher. And in order to see how dangerous it will be, this higher CG can be again, the simulation can be done by raising the angle. Okay, so this is the reason why we want to raise the angle. We want to see if passenger sits on one side or the passenger majority sits on the upper deck, how it will affect the stability of the vehicle. And that is the reason why we need to test the bus through a greater lift. Okay, is to account for CG changes as the vehicle travel. Okay, you help me jot down these two possible reasons, either tilt to one side or raised CG. All right, let's take a look at C. Okay, the property of which liquid transmit pressure equally on both sides. So it's able to do it because it is not compressible. And because of this, it's able to transmit pressure equally throughout the liquid. Okay, that's all. Okay, for C part 2, maybe you can help me calculate this. The value is 84,000 newtons. Yeah, let me know if you can get it. So I can do something like this. Pressure at the master equals to pressure at the slave. The master pressure will be force over area 360 over 0.0012. And then the other side will be the force over 0.28. Yeah, then you should get 88,000. Yeah, 84,000.
Oh, I think because I multiply instead of divide.
Ah, okay, it's the PF over A thing. Okay. Yeah. Okay, so this will be my working. So we are going to use okay, we're going to use this. So for the effective index given to us 1.6, 3 times 10 to the power 8 over the speed of light that we want. Then from here we get 1.910 to the power of 8 meters per second. Then this one is the same thing, 1 over sine c, 1.6, 1 over sine c. When we do the math, we should get about 39 degrees. Yeah. So no issue for this. Yeah, can we try to complete the diagram for B part 1? I'll read this here first. Image. So for the image, I'll use in blue. This line itself that passes through the center of the lens. This line will give us the position where the image is. Okay, so this will be locate the image eye. To locate focal point, we'll go parallel. And then cutting through the image. This point here will be our focal point. Yeah, so these are the two information that we need. So triple I asks us to describe one significant change if part of the lens is broken and only the remainder is used. So common mistake is, let's say part of the lens is gone, then part of the image. Okay, in fact, let's put it this way. Let's say I have okay, let's say I put a cardboard over here. Okay, let's say I put a cardboard over here. Kaylee, what's the direct impact to the image? Opaque cardboard.
The image can still be seen.
Yeah. So one of the misconceptions is I always get answers that says some part of the image is gone. Okay, that's definitely not true lah, because there are many light rays that will hit the image. So one of the best example is the bottommost light ray that's given to us. You see there is altogether 3 light rays that is shown over here that actually converges to give you the image. And that's only because we only draw 3 light rays. They are like infinitely a lot of light rays that's going to converge at the image. So by saying that the some part of the image got cut off is entirely wrong. So since we mentioned that the image can still be seen, but what will be the difference then if we actually block off some of the light ray to reach that they can reach the image as a result of the cardboard? If only some of the light ray can reach. This has same impact as the lens, some of a part of it got broken off. That means it can no longer capture the some of the light rays. It's the same as putting a cardboard there. The impact is the same. So something will happen to the image. It becomes with lesser light ray reaching the image.
Is it becomes dimmer?
Yes. Okay, it is always becoming dimmer. It will not become less sharp or more sharp or part of it disappears. All these are wrong. So in this case, we'll say that the image becomes dimmer. So based on this, when will the answer be the image becomes more sharp or less sharp, right? It's normally when we shift, for example, right? Let's say I have a screen over here. Okay, so you can see that in this case, the image that's captured on the screen will be a non-sharp image. Because you can see that the black line from the question, the blue line that I drew, the red line that I drew, it casts the image of the top of the arrow, right? It casts it at 3 different positions. So all these images will overlap each other. And the overlapping of all these, this overlapping of all these 3 images, for example, will cause your image to be blurred. That's why we need to adjust the position, either of the lens or of the screen. So one way to make it sharper will be to increase the sharpness of the image. We will need to shift it. Okay, we need to shift the screen to the left until it reaches this position. So it aligns with where the light ray all converge. So do remember when there's a cardboard blocking or part of the lens is broken, it is always like what you mentioned, it's the brightness of the image and not the sharpness of the image. As long as you put the screen at the right position, it will be sharp. Okay, so one adjustment can be done to produce a smaller image. So in order to produce a smaller image, we remember that when the object distance is more than 2 times away, they will be smaller than the object itself. So if you want the image to be even smaller, so one of the ways is to move the lens further away from the object. So there's 2 things that we can do. The general idea, okay, is to increase the distance between the lens and the object. Okay, as we can see from the lens setup, anything more than 2F, for example, it gets diminished. And the further you pull, the smaller it gets. So the two ways to do it, number one is either shift the object to the left, or we can shift the lens to the right. But the general idea is always to increase the distance between the two of them if you want the image to be smaller. And if you want the image to be larger, we put them closer together. So as we can see, the belt becomes negatively charged because over here it mentions the belt rubs against the rollers and becomes negatively charged. So when it becomes negatively charged, uh, likely to gain electrons from the roller. Okay, so really straightforward. This is charging by friction. Something like this. Okay, for part B, okay, we already have the Earth, so if we remember this, with a positive, negatively charged particle with a neutral metal sphere, you will see that this one becomes plus and this one becomes minus. And as a result of the earthing process, the electrons will run down. So eventually, what we will get will be a scenario that looks like this with the earth wire around it. So because of the loss of electron, this thing here is now positively charged. Okay, exactly what we want from here. So when we mention about positively charged, we always want to talk about as there are more positive than negative charges on the object. It's something like this. We draw the charges, actually, we accidentally draw it here. It's actually this setup here. So we can just draw a few charges here already. Okay, so again, we know that this is overall minus overall plus, so there is an electrical field that goes this way from the positive to the negative. So electrical field we define as the region okay, where this electrical charge experiences a force. Okay, if no question for this, let me try out D part 2 for the calculation. So working wise, it's just Q equals to IT 0016 10 to the power negative 3 because of the milli over here. Currents times 0012. So my current will be 0.0013 ampere. Something like that. Okay, let's define potential difference. So this is this make use of the formula V equals to E over Q, where this is a joule per charge. So this will be how many, if this is 6 volts, then it will be 6 joule per 1 coulomb. So it's basically the amount of energy to push or to drive 1 coulomb of charge through, in this case, it's a resistor. I'll just put resistor. So 9.6, we need to explain 9.6. So this means that 9.6 joule of work is done to drive. Okay, we can use the term unit charge. It also means 1 coulomb. Let's change the narrative. If let's say the question is asking for explain what is meant by the EMF is equals to 12 volts, something like that. Then I will say that 12 joules of work is done to drive a unit charge through the, instead of resistor, because it's EMF, it will be entire circuit. So both of this, this single definition can be explained, can be used to explain the PD and EMF. So first of all, I'll find current passing through the resistor. So the voltage given to us through the resistor is 9.6 over 40. Then from here we get 0.24A. So the current passing through the bulb is the same as current passing through the resistor. So therefore, this is also 0.24A. So power, we have, here we can use I square R. Light bulb current is 0.24. We square it. And resistance of the light bulb is 10. So from here, we get about 0.58. This is 2 dB. Okay, but normally we can also do it 3SF, it's fine. Okay. Okay, generally, for questions like this, the steps is always very standard. Okay, but before I give you the answer for this, right, can you take a look at the scenario and you let me know if the brightness is increasing or decreasing. An easy explanation for brightness. Okay. Schools sometimes will say voltage increase, brightness increase, or current. To be very safe, brightness of the lamp, the safest way for you to gauge is power, because power is defined as joule per second. So for the same period of time, if you have larger power, that means you are generating more lights. Okay, let's do for power calculation, we know it's I times R. So let's do a simple experiment here. Let's say this is a 2 ohm resistor with a 2 ohm light bulb. Okay, this is 12 volts. So if you do a quick calculation for this, right, we can see that the current flowing here is 3 ampere. And then this thing here is 6 volts, 6 volts. So for this setup here, the power of the lamp is equals to sorry, not IR, sorry. It's IV. So the current is 3, the voltage is 6. So this lamp here produces a power of 18 watts. Now what happens if the resistance of the lamp remains the same, but the resistance of the resistor increase or decrease? So Kaylee, can I give? Yeah,
Can I change my answer to it will become brighter?
it becomes brighter, it does. Yeah, it does become brighter. So let's talk about the other side. What happens is that mathematically, if this now decrease to 1, this is 2. Okay, Kaylee, can you help me find the power of the lamp in this situation? And for the third situation, let's say the other side, the resistance increased to 4 compared to the original. The lamp is still the same. Can you help me calculate the power in each case? Everything remaining the same. The only thing that we change here is the resistance on his side. Then from here, we can see the effects of changing resistance on the side to the impact on the brightness of the lamp. But you are correct, it actually becomes brighter. So the current here will be 4A. Then you have 4 volts, 8 volts. This one is 4 times 2, 32 watts. This one, the current is 2A. 8 volts, 4 volts. This one only 8 watts only. Make sense?
Yeah, makes sense.
Okay. What is the main thing that we want to bring away from here? Okay, you notice that in all situations, the lamp has the same resistance of 2 ohms. Then in scenario A, when the resistance of the resistor drop, his potential difference also dropped to 4. And then the lamp actually draws more voltage from it, even though the lamp remains the same. In scenario B, you notice when the resistance of the resistor increases, he draws more of the voltage, whereas the lamp, which again remains unchanged, it is now drawing only 4 volts compared to the original 6 when they are equal. So the most important conclusion here is that this occurs, right, in particular in series circuit. The larger the resistance of the component, the higher the potential difference across it. Okay, so everything else remain the same. The larger your resistance, the more voltage you will draw. The lower your resistance, also the same thing, the lower the PV of the object. So let's talk about the question again. When you put an additional resistor R across it, okay, so this part here, no matter what value of R is this, by adding an additional branch line, okay, the addition of a branch will effectively decrease the resistance across the 2 points. That means this previously it was 1040. Okay, before R was introduced, it was 10 ohms over here, 40 ohms over here. Now with the introduction of a branch and a resistor on that branch, this overall portion here, the resistance will drop. So like what we've seen here, in a series circuit, if the resistance drop, the PD that it draw will also be lower. And we can also see in our scenario over here, when the other side resistance dropped, the power actually went up. So when the power went up compared to the original case, okay, this is your original case, you'll notice that the lamp will become brighter as a result of this. Okay, so using this as our background information, I would say that R actually decreases. The effective resistance across the parallel circuit, which is this part here. So because his resistance dropped, remember the EMF stays the same. So because this part here, the resistance dropped, I would say that the potential difference across the parallel circuit decreases. Okay, this is based on the concept that the lower the resistance, the less voltage you will draw. And because the EMF is still the same, therefore the potential difference across the lamp will increase. Okay, just like the original, it was 6 volts, 6 volts. Then when one of the resistance drop, this one is a similar case to our question. The other side draw more voltage, same idea. So in this case, hence the don't need to talk about the power rise and all. So as long as we know that this thing happens, just mention that. Hence, brightness of the lamp will increase. Okay, this is the entire setup.